Fine. If anything, you can use the chat box or thumbs up emojis like that so that we can interact also meanwhile. Fine. Actually, what is the actual plan? Let I will first explain with you peoples so that we can follow that plan. So my plan is from today and tomorrow. This 2 days will be like 1 hour classes only, right? From next weekend, this will be going to be a 3 hours classes. So probably in this week, I will complete combination circuit. Means today and tomorrow. After next week, means from next week onwards, what we will plan, we will cover sequential in first 3 hours, and from next part means Sunday 3 hours class will be very long. So we will start very long from next week itself. Okay. So this week we will focus combinational and we will complete combinational fully. Fine. So in previous class, what we have discussed about number systems, right? Different types of number systems we discussed, and what are the positional weight for each number systems. And we also discussed about binary number system in detail, in depth of binary number systems like ones complement, two's complement, signed magnitude, what it means, how we will represent. So what are the drawbacks over there and why we are using two's complement, what is signed and unsigned category, everything we discussed. I hope so. So today, the continuation of that class, yes, still we have conversions, right? So at the end of the class, I will tell about the conversions, like from one number system to another number system as a quick revision like that. So we will straightly start from codes, okay, in digital electronics. I hope Anjali ma'am will record this session. Fine. So codes. Okay, ma'am. So in digital electronics, particularly while we are speaking about datas, right? So while we are datas is nothing but like we are transmitting from one end and we are receiving at another end. That data can be represented in different way, like in number systems, different number systems we have, and we said like which is more easy to use, right? Even we have different types of codes. Codes are nothing but group of symbols. So generally we have different types of codes. Weighted codes. So our binary number system is also a weighted, like weighted code, non-weighted code, reflective codes, sequential codes. So still more like alphanumeric codes, and finally error direction codes we have. These all like a different type of codes to represent. These are like terminologies they are used to represent different types of symbols. If you consider alphanumeric codes, so ASCII, like American Standard Code for information interchange. So they are using this. They will represent everything in 8 bytes of data representation, right? So if you go for weighted codes, we have BCD code. So BCD codes are also called as 8421 code. Okay, these are our weighted codes. Weighted codes means this will contain positional weightage. Positional weightage. That is the reason instead of calling BCD, they will call as 8421 code. 8421 represent the weightage. Using the weightage itself, they will describe this code as 8421 codes. We also have non-weighted codes, XS3 codes, gray codes, this and all non-weighted codes. Okay. So these topics are very important actually. This kind of coding techniques we will utilize in different part of our course actually. Example, gray code is also one vital code which we'll utilize in CDC techniques itself. Okay, in CDC technique, while we are using asynchronous FIFO to getting data to be correctly transferred from one clock domain to another clock domain, we will use the gray code concepts and all that. We will discuss this later actually. So those which are very efficiently utilized in our Verilog, CDC or STA techniques and all, we are discussing those concepts in depth in the digital electronics itself. Okay, so that it will be quite familiar while we are working on that part. Okay, and we also have reflective codes. Again, XS3 is also an reflective codes. We have sequential codes. BCD code is also called as a sequential codes, means the values which we are representing will follow a sequence like 0, 1, 2, 3, 4, like that. Okay, so these are the different types of codes we have. So we'll slightly start with the weighted codes, non-weighted codes and all. Okay, so I will explain what reflective codes is also called as self complement codes. We will discuss in depth. Okay, so BCD code, as the name describes this code feature, this is nothing but binary coded decimal, right? That means we will derive the decimal digit using 4-bit binary. Okay, so we already know in decimal number system we will have 10 values, 0 to 9. That means 10 decimal digits we have in decimal number system, right? So here we will derive everything like in BCD in binary, 4-bit binary we will utilize. 4-bit binary will utilize to represent 0 to 9, right? So the order will go from so this will nothing but a decimal part, and this is nothing but your BCD. So you will have decimal number like 0, 1, 2, 3, so on up to 9. And here the equivalent representation in BCD for your decimal will be done with 4 bits. So 0 you will represent in 4 bits, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, so on up to 9 means 1, 0, 0, 1. Right. So these codes are called as valid BCD. Okay, these are called as valid BCD, as you are only representing the equivalent 9 decimal values in BCD, right? Decimal digit. But there are some invalid BCDs is also there. Invalid BCD. So what is invalid BCD digits? Nothing but it starts from 1010 all to 1111. So these all are called as invalid BCD. Why? As we are using 4 bits to represent our decimal values, the maximum combination while you are following 4 bits is nothing but 2 to the power 4. This is equal to 16 combination is possible. But out of 16 combination, only 10 combination I am utilizing to represent our decimal digit. So remaining 6 combination is invalid BCD. Okay, so if someone is telling there is nothing like 1010 in BCD representation, that is absolutely wrong. Okay, so then what actually 10 means? See, for example, so this is nothing but 10. Okay, so to represent 10, we want to treat how this is one decimal digit and this is one decimal digit. So one should be treated with one decimal digit. One decimal digit means for one, what is the value? Equivalent value is nothing but 0001. And for 0, again you want to represent with one more 4 bits. So totally, you are utilizing 8 bits to represent value 10, decimal value 10 in equivalent in BCD, right? So literally, this is not actually a good way of representation. Why? If I go with normal binary representation, for representing 10, I require only 4 bits. 4 bit is sufficient to represent. Even up to 16, it is 4 bit is sufficient, right? So hardly we won't use in our technique, but this is just a technique where they will use while transferring some data from TX to the receiver part. So they will do some techniques to avoid noise. So this kind of things. Okay. So in general, inside our digital electronics, digital portion of our VLSI, we won't utilize this more. But the gray code have a vital role. More we use gray code. Okay, only this thing you want to understand, and the complexity of doing addition also get little bit hard while you are using BCD. I will explain how and why everything. So normally this is similar like anything like 17 in decimal. If you convert, you want to treat everything as a single decimal bit. Okay, decimal digit actually. So now we will do some conversions quickly. Like if something is in BCD to decimal, what how we want to treat? Simple. This is nothing but decimal to BCD conversion. So previous example 10, which we have converted 10, and now 17 is nothing but how we will write. 1 you want to treat as 0001, and 7 you want to treat as 0111. Okay, so in 4 bits. So this is the equivalent representation of 17 in BCD. So reverse how you will read, nothing, same actually. If you have something like 0001 0100, uh, you want to consider 4 bits. This 4 bits is nothing but value 1, and this 4 bit combination is nothing but 4. So the given BCD number is the equivalent representation of 14 in your decimal. That's it. And some terminology they will put into the picture while they are telling packed BCD and unpacked BCD. So packed BCD is nothing but, so all the value which you are packing should come less than 9. Okay. Sorry, greater than 9. Greater than 9 is called as packed, less than 9 is called unpacked actually. For example, let I have 1, 5, 6, 10. Okay, so these all are packed BCD. If you convert it into into BCD, you will represent each decimal digit with 4 bits, right? So 0001. For 5, you will represent 0101. For 6, you will represent as 0110. Okay, so the values which we have here is 1, 5, 6. So each decimal digit is not greater than 9. If it is greater than 9, it is packed. If it is less than 9, it is a unpacked BCD. This is just a terminology they are using. So and best usage is compared to, so if we compare binary versus BCD, which one is good? See, BCD is less efficiency. I already said, because we want to, bit growth is there. There is a concept of bit growth. So it is unpredictable. But in binary, it is easy to understand the bit growth concept while you are doing addition, everything. Bit growth is easily identifiable. So it is easy to use anyway. What is bit growth? For example, if I add in binary 4 bits plus 4 bits, so what will be the bit growth? Like what will be my output? How many bits are sufficient if I add 4 bits? So anyone can, you can use chat. The question is simple. If I add 4 bits, okay. my output value, how many bits it is going to utilize? 5 bits. Exactly. Right. Because if you use maximum value in this 4 bit and maximum value in this 4 bit, your output will be in 5 bits. Right. So, but if I do like this, there is 4 bits, 4 bits, 4 bits, 4 bits, 4 bits. Like I'm adding all my 4 bits, 4 bits, 4 bits. Like 7 times I am adding. Then this time, how many bit growth will be there while doing my addition in binary number system? 7 times if I add directly. Okay, so this is very important because in our RTL design, we will deal with this kind of stuffs. Okay, adding the bits and all. So if you are adding, you are doing A plus B plus C plus something you are doing in your RHS side, some, and if you are assigning to LHS side, the bit width of this LHS side should be calculated properly, or else you won't get the precise sum answer, or else some data loss will be there, right? So that's the reason I am forcing more concepts in the digital electronics here itself. If you do 7 times of same bits, if you are doing addition, the bit growth will be 3. That means 3 plus 4. Okay, so normally if you do one time, one bit growth will be there, means this will be in 2 powers, 2 powers. Okay, 3 times will be there. So see, 7 times I'm doing, or 8 times if I do, so 2 power of 3. Okay, this is 3 represent, this is equal to 8. How many times I am doing? So this is nothing but your bit growth, how many bits it will be getting growth at your MSB side. Okay, if I do 16 times, then nothing but 2 to the power of 4, means if I add same bits for 16 times, the maximum bit growth will be 4. Okay. Actual bits plus 4. Got it? Huh? You can use thumbs up or anything. Or else I will repeat it one. Okay. So this is how the bit growth while you are doing additions. Okay, for subtraction, while you are doing subtraction, bit growth won't be there, because or there itself you are subtracting the values. Okay, adding time bit growth will be there. During subtraction, bit growth won't be there. Multiplication, yes, bit growth will be there, and this is familiar by everyone, right? Uh if you just add 4 into 4, so your bit growth, how much it will be there? For to represent 4, for example, you are using 4 bits, assume, just for an assumption, 4, again, for value 4 you are using 4 bits, and your bit growth will be 8 bits. This is straightforward. You will add a plus b here while you are doing number of bits in A and number of bits in B. So 4 plus 4, 8 bits are required while you are doing multiplication. This is very straightforward, and I will be explaining some few things about this addition, subtraction, how it will, the bit growth, everything, using Vivado software, where I will also explain you about some IP cores while we are doing some designs on them. Okay, most familiarly used the IP cores. Okay, I will be planning, if time permits, I will give you some idea about a FFT IP core, filter IP cores, some DDS, some BRAM, BROM, some, already we have some default FIFOs also. I will explain you the utilization FIFO, all this adder, subtractor, everything. Okay, so again we will jump into our discussion. So the binary is predictable. What I'm trying to tell you here is easy to assume the bit growth, easy to guess the bit growth, everything. But in BCD it is very complex. It's not easy. So let quickly we'll see some operation. There is some rules you want to follow in BCD addition. We will see some BCD addition. I will tell some what is the complexity over here. If you add some number and the sum value, if your sum value is less than or equal to 9 and your carry bit equal to 0, then this is the correct answer. If your sum value is less than or equal to 9, and the same scenario, if your carry value is 1, okay, this is incorrect and we want to correct it again. I will tell why incorrect and how we want to correct. And if your sum value is greater than 9 and also you got the carry as 0, this is also incorrect. So we have two incorrect. So we will see this example quickly so that you can understand. Let for first example, let I will take the value 2. This is the decimal, in decimal value 2, and I want to add with the 6. So first of all, I want to represent this 2 in BCD. 2 in BCD is very straightforward. 2 in BCD is 0, 0, 1, 0. And 6 in BCD is nothing but 0, 1, 1, 0. And if I add this 0, 0, 1 carry will be there, 0, 1 carry will be there, and 1. And there is no carry actually. So I will put 0, there is no carry. And this is your sum. Sum value is nothing but 8. And sum value is less than 9, means sum value which I got here now is 8, which is less than or equal to 9. This condition satisfied and I got carry equal to 0, and this is correct answer. And simple, 2 plus 6 is nothing but 8 and you got 8. So there is no tricky thing is happening while you are doing this BCD addition. But let me consider one more scenario. 3 plus 7. Everything I am telling here in the decimal format only. Decimal value 3 and 7 if I want to add. First I want to convert the decimal to BCD. So to represent 3 in BCD, there is nothing complex, straightforward, 0, 0, 1, 1. To represent 7, what we will use? 0, 1, 1, 1. Now if you add this 0, again there will be carry, 1, 1, again 0, 1, 1. Okay, ultimately we won't get any carry 0, but the value which you got is nothing but 10, right? So what I'm trying to tell, in BCD representation there is no 1010. This is also called as invalid BCD. I already mentioned. That is the reason I am writing this condition. If you remember this condition, it is good enough to do other problems. The value which we got is 1010, 10. So 10 is, say 10 is greater than 9 and I got a carry as 0. Yes, of course I got a carry as 0. This is an invalid case. So what I want to quickly want to do, so I want to add plus 6 to this 10 to get the proper result. So I will tell quickly why plus 6 also I will explain within a minute. So give me a minute. So I took just this output 1010 and I'm just adding plus 6 to this. So plus 6 is nothing but 0, 1, 1, 0. So I got 0, 0, 1, 0, 1, 0, 1. Okay. So this is one 4-bit and this is the bit. Okay, so if you do, this is the equivalent representation. What I got output here after doing plus 6, I got 0, 0, 0, 1, 0, 0, 0, 0. Nothing but carry also I took and I represented in 4 bits. Okay, and this is nothing but 1 and this is nothing but 0. Nothing but 1, 0, 10. This is the BCD representation of your value 10. Okay, so as there is no direct 10 representation in BCD, you want to do plus 6. Again, why plus 6? I already said you have 10 valid BCD and 6 invalid BCD. That is the reason to get your valid BCD, you are adding plus 6 so that you got a valid BCD. So this is this case, third case I explained. So any doubt in this? I hope there is no doubt you got it. If yes, you can give one thumbs up. Or else I will repeat it, no problem. Fine. So this is all about this case. So one more thing. So if you are doing like adding 8 plus 9, okay. So what is the equivalent represent of 8 is 1000. We have a valid BCD representation for your decimal digit 8, yes. And we also have a valid BCD representation for our decimal digit 9 also, which is nothing but 1001. Now if you add this 100, and you got carry 1. So here you got carry, and the sum value whatever you got is 1. Okay. So it falls under which category? This category. Means sum you got 1. So 1 is less than 9, and you got output as carry bit as 1. Okay, this is also incorrect output. So we want to correct it. Why incorrect output actually? So 8 plus 9 value is 1. No one will accept. Right? This is stupid. So again, what I want to do to my output 10001, I want to add plus 6. So 0, sorry, 0110. So 11101, right? So this is nothing but in 4-bit. Okay, this is in the 4-bit 1, and this is the 7, right? 17, and 8 plus 1 9 is 17. So this is how actually we will represent. 1 minute. So this is how we will represent 17. Got it? Huh? So you can clearly observe the complexity here. It is more, very more, right? So next code is XS3 code. If there is no doubts in this, we can move to next code. Abhishek, okay. Thank you. Next is nothing but, 1 minute, XS3 code. So XS3 code is unique code. Like this is unweighted code. It comes in the category of unweighted code, and we will use everything here also 4-bit. And one more advantage of this is also a self complement, means reflecting codes, self complement codes. So I will quickly tell what is this and all. So how we will achieve XS3 code means for any given decimal digit, you will convert that to BCD. That BCD, again we will add plus 3 to that BCD to get our XS3 code. Yes, again the step is more, complexity is more, but just I am recalling the concept here, what we are actually doing. Example, like we consider value 5, which is in decimal. Now the BCD equivalent representation of your 5 is nothing but 0101. Now the same value 5 in XS3 is nothing but you want to add a plus 3 to this 8, right? So here you will get nothing but 1000. Again you need to, you can put the addition and you can do, but you will get finally 8 value. This is the XS3. This is nothing but value 5 in XS3 representation. Okay, so like that we will have something that I will write quickly. This is decimal, this is BCD, and this is XS3 form, right? Now nothing but I will write some values 0 1 so on, and you will get 8 and 9. For 0, BCD is 4 bits. Everything we will represent 4 bits, even in XS3, right? As I am representing 4 bits in BCD, so in XS3 also it carry over with 4 bits one. So here also 0001. So for 8, 1000, and for 9, 1001. So if I add for 9 plus 3, that is the equivalent representation in XS3, right? If I add plus 3, what is the value I will get? 1100, 12, right? If I add plus 3 for 8, I get 11. So 11 can be represented as 1011. So for 0, the first value will be 0011, and start with 3, and for 1 I will get 4 is plus 3, 0, 1, 0, 0. And this is also called as self complement code. How this is called as self complement code? If you consider the value 9 in excess, this complement value is nothing but 0. You can see 1 1 0 0 here, 0 0 1 1 means self complementing. If you consider the value 8, which is nothing but 1 0 1 1, and if you look into the value 1 9 9 9, correct, correct only. Like 0 means 1, 1 means 0, 0 0. Yes, correct, correct. Self complementing. Okay. So, like everything will be in self complement form in XS3. So, generally, uh, if any values is given 24 or something, if it is given, first you want to represent this in BCD. So BCD is 0 0 1 0, and for 4 what is the BCD value? 0 1 0 0, and you want to add plus 2 to this, sorry, plus 3 to this to get the equivalent XS3. So 0 0 1 1, if you add you will get value 0 1 0 1, and for this 0 0 1 1, and if you add this 0 1 1 1. So this is your equivalent representation of value 24 in your XS3 code. I hope you got this. So only few things you want to remember while we are discussing XS3, like we will add plus 3 to your BCD, and this is self complement. There is no weightage represent for your positions, so there is no positional weight. One that thing you want to remember. And here also addition will get a little bit trickier while you are adding the numbers. Like I will tell you, because you will add with XS3, each digit you will add with XS3, right? Means if I add 2 plus 5, so uh, you want to represent 2 in XS3, means 2 plus 3. 2 plus 3 is the equivalent representation of value to do 2 in XS3, right? So 5 is the value. So 0 1 0 1. For 5 you want to add plus 3, means the value 5 in XS3 is nothing but 8. 1 0 0 0. And if you add this 1 0 1 1, so the output which you got is in XS6 form. XS6 form. Okay. Means you did 5 plus 8 and you got output as 13. So there is XS6 in this, but I want to represent in XS3, right? Output also you want to represent in XS3 only. So there is XS6. So I want to remove one XS3 from your output of XS6. So 1101, I want to minus 3 from this. So 0011. So I want to neglect minus 3 so that I will get the value called 10. 10. Okay. So again, don't get confused. 2 plus 5 is nothing but 7. 7 value, to represent the value 7 in XS3. XS3, nothing but 10 is the value actually. Okay. Because we will add plus 3 to 7 to get an equivalent value in XS3, which is nothing but 0 1 1 1. Right? That is the reason, but in our output we never got this value 0 1 1 1. So what is the reason? The output will contain XS6 6. That is the reason we are neglecting 1 3 and we are getting the output. Then we will get the output as 0 1 1 1. Okay. So again, you don't get confused here. There's some complexity is there while we are dealing with your XS3 BCD and okay. Got it? Understand? Abhishek, Bogala. I think Amar didn't join today. I think so. Fine. Any confusion is there, I can repeat it once again. If not, we can continue. Yes, from XS6 we want to subtract a 3 to get your actual output. The reason simple, see Abhishek, actually 2 plus 5, what is an output? Normally 7. So simply how we will represent value 7 in XS3, leave about everything. XS3, what is the value? So to get assume that the value which we got 7 is also decimal, because I did direct decimal addition. So 2 plus 5 is 7. So 7 is in decimal. To get in excess, first I want to convert this into BCD. In BCD 4 bits, what is the value for 7? 0, 1, 1, 1. So this is the equivalent representation of your 7. So for this 7, you want to add a plus 3 to get a in excess 3. So which is nothing but 7 plus 3 is again 10. So you will get answer this one, 1010. Okay. But this is the equivalent representation of value 7 in excess 3. But here what happened? See, I have took a value 2 in excess 3, which is nothing but 5. I have took a value 5, decimal digit 5, equivalent representation in excess 3. After adding, I got an output which is in excess 6, means I didn't get output 1010. Okay, 1010, 7 is expected here, but I didn't get 7 here. So I know there is a one more 6, say one more 3 is added in our output. So I want to remove that actually. So 1101 minus 3 I want to do. This is nothing but 13, right? 13. So 13 minus 3 if I do, I will get output as 10. So 10 is nothing again, but it is the equivalent representation of value 7 in x3. Got it, Abhishek? Ah, exactly. So here also addition becomes complex only. There is no like smooth way of addition. So next code is nothing but gray code, and this is very important. Many areas we are utilizing this gray code effectively. Even our in Kmap, I think you heard about. I will explain Kmap also today. So Kmap, this Boolean algebra, these are the ways we will reduce our expression. To simplify our expression, we will use. So in Kmap also, we will utilize this gray code effectively. Even for synchronization, we will use this gray code effectively. Okay, these are all one technique. So gray code is also called as reflected code. So one important thing in gray code, each consecutive values, only one bit change will be there. Only one bit change. Okay. So this is, I will tell what this one bit change. Okay. Unweighted, this is also called as unweighted code. Okay. So the switching operation, there is a less switching operation, as there is only one bit change for each consecutive value change. Okay. So this will reduce your switching operation. Switching operation, you can tell power consumption of everything is reduced. This is one optimization method also. Okay, they can name this gray code as some unit correction code, or minimum error code. Okay, minimum error code, all the names are to represent the gray code only. So first uh, I will write some gray code, okay, quickly, the binary and gray code, so that you can understand how much bit toggling is happening for a gray code. And this, for example, let me consider value 3 and 4. This is some decimal. For decimal, three value equivalent representation in binary will be 0011, and for value 4 in binary will be 0100. Right, this is nothing but a consecutive bits actually. So it is coming in sequence after 3, after 4. This is the next value bit. So for next value itself, how many bits are toggled? You can see this is the least significant bit. 1 is also get changed in our binary, and this bit also toggled. This is also toggled, and only this MSB remains without toggling. So we have a switching process happened 3 times here while we are considering the data representation in the binary code. But if you go for gray code, I will tell how to convert binary to gray. But for time being, first understand this. This is the equivalent representation of 3 in gray code, and this is the equivalent representation of 4 in gray code. So you can see the LSB bit which is remains as it is, and next position also remain as it is. Only this bit is getting toggled from 0 to 1, and this remains as it is. So there is always only one bit change while you are considering two consecutive values. Okay, so this is the actual advantage of using your gray code. This makes more problem with less solution. Means we have more problems and we will achieve all the problems using the same solution. Okay, it can fit with multiple problems. So again, now we will directly jump into the conversion, how I did this binary to gray quickly. So this should be very clear and understandable, so I will explain it clearly. So 1011, assume this is our binary. So this I need to convert it to gray code. So while you are doing gray code to binary or binary to gray code, one thing you should be keep in your mind, MSB part you are not going to disturb. Means you want to keep MSB part as it is. So in both the conversions, gray to binary or binary to gray, so this MSB part I will be maintain as it is as well. Now what I will be doing, right? This bit again I will consider 1 here, and I want to add this one 0 plus 1, and I want to only consider sums. I want to neglect the carry part. So 0 plus 1, again 1, so there won't be any carry. Again this 0 is there, right? Next bit of your binary you want to consider for your next addition operation. So 1 plus 0, again you will get 1 only, there is no carry. Then I will take next bit 1 here, I will add here. So 1 plus 1, yes, my sum part is 0 and my carry part is 1. Only I need to consider is my sum part. Okay. So if you remember, for I will tell these things later, for doing addition to get only sum, XOR gate is utilized to achieve the sum operation, right? XOR is also called as odd one deducted. If there is only one is there, nothing but if you remember the truth table 0 0 0 1 1 0 1 1, the output will be 0 1 1 1 0. Means whenever there is odd number of ones in a given input, your output will be 1. Okay, so we are effectively doing XOR operation here for your binary digits. By one binary digit we will consider, and we will do XOR operation to get your output. So this is nothing but equivalent representation of your binary in gray code. Okay, so how I can summarize this equation means, to get my gray code, uh, so G3. So I will write these are B3, B2, B1 and B0. This positions I'm telling, and this is nothing but G3, G2, in gray code we got, right? G1 and G0. So if you remember, G3 is straightforward. G3 is equal to directly nothing but B3. Simplifying the equation. Okay. So what is about your G2? G2 is nothing but again you want to take B2. So B2 bit and you want to do XOR operation with the what bit? B3 bit, right? Again, if I consider G1, so this is your G1. For G1, you consider B1 bit. So yes, B1 bit XOR with B2. Again, like G0. So G0 is nothing but you want to consider the B0 bit as it is, and you want to do XOR with what? B1 bit. So exactly these things we will do in Verilog coding also. Okay, this kind of equation, and we will do these things in your data flow modeling in Verilog. Okay. So this is all about gray code and binary to gray code conversion. So gray code to binary conversion is also simple. Like I will put those point here itself. Give a minute. So for example, given example, this is the given example 1110. I already said whatever the conversion you want to record your MSB as it is. So I am not going to do anything with my MSB. So I will record my MSB as it is 1. Now what I want to do, the output which you got in binary, right? You want to consider that here for your next process. So here also you will do XOR operation only. So 1 1, your output of XOR will be 0. So again this 0 I will consider here. Okay, so 1 1 0, here you will get output 1. Again this 1 I will consider over here. I will do XOR here, 0 with 1, again you will get output 1. So this is your binary representation of a given gray code. Again you can simplify this thing. uh, this is nothing but your B3, B2, B1 and B0, same how we have derived the equation, right? You can also derive for this conversions. I hope gray code concept is also clear and straightforward. Okay, so next thing is like min term and max term things also I will cover. Min term and max term. See, this is nothing but way of expressing your digital equation output equation. That's it. Okay, this is a different way how we can represent our equation, output equation of a given digital circuit. So, what is min term? Min term is nothing but SOP, sum of product. What is your max term? Max term is nothing but product of sum, right? Let me consider some example. XOR example itself we consider. We know two input XOR will have two inputs, which is called as A and B, and you will have an output Y, which is nothing but XOR output. So 0 0 0 1 1 0 1 1. Now this is one circuit, and output of this circuit we already know, right? 0 1 1 0. Just now we saw in gray code, this is nothing but odd one detectors, right? So now we will write min. What is the min and what is the max? So min means I already said SOP, sum of product. This is product of sum. And one thing you should remember, the terminology in sum of product, value 0 should be complemented. Means if 0 is there, you want to make us complement like 1. In POS, if 1 is there, value 1 is there, you want to complement the 1. Okay, I will tell what actually this means. So here the input, what is the input? 0 0. So I am writing this as A bar dot B bar. So why again I'm using dot? Because we are doing sum of products. We are finding the products. After finding the product, we will do sum for our products, right? So the ultimate aim, the end letter in SOP is P, which is nothing but product. So you should make sure we are doing product every time. Now If there is a 0 in your input, you want to complement it. That means your input A should be complemented. So A bar dot B, 1 is there, so I am representing same as it is. Again, for here, what is there? A is 1, so I am directly writing, and B value is 0, so dot I am complementing B bar. Here both values 1, so I am just writing A dot B. So this is the way in min term we will write. So while we are jumping into max term, your end letter is S, which represents sum. We are doing finding sum. After finding sum, we will do product of all your sums. Okay. So now the concept is simple. If there is 1, then you want to do complement, or else you want to write as it is. So 0 and 0, you won't do, not need to do complement. You want to write as it is. So A, I will use plus in between instead of product dot. So B. Okay. And for this, A plus B bar. A plus B bar. For this, what I want to write? A bar plus B. And finally, for this, what you will write? A bar plus B bar. Fine. But ultimately, based on your outputs, we will consider those part only. So where and all my output is one high value, only those expression I will consider. So my output y is high for value, like this is equivalent representation of 0 1 2 3 input combination in decimal form I wrote. So for 1 and 2, my output is 1, right? So only these expression I will write. If you remember, in XOR get, what we will write? A equal to A bar dot B plus AB bar. This is how generally we write the expression. So all things we are generally used to represent with SOP only, sum of product only. So if you represent in product of sum of, that is not, it won't affect anything. This is also same only. If you consider this expression, A plus B bar, again A bar plus B. Okay, so this is also correct. There is nothing wrong with this also. So both are correct if you apply some value for A and B, and if you have observed what is output of Y in this function and in this function, both you will get same only. Okay, you can do this as an homework. So ultimately we will always use SOP form of representation only. So generally, then what is the function? How you will write minterms here? So minterms are represented by using summation symbol. So function y equal to sum of your minterm. So what are the minterms over here? So in 1 and 2, it is actually high. So I can write 1 comma 2. Okay. So this is our minterm. Oh, sorry. Actually, for max term, you want to consider the value 0 section. For min term, so where and all it is 1 there, we want to consider that expression. For max term, so where and all zeros there, 0 as your output, you want to consider 0. So that means this and this you want to consider. Okay, in your expression. So for max term, what is the function? So function y equal to max term is represented by the value pi. So pi max, so the remaining function, so wherever it is 0, so decimal value is 0, and here output is 0, so this value 3. So 0 comma 3 is your max term. Okay, so that by using this we can represent. Mostly we will follow only one methodology, which is nothing but SOP form of representation. So now for given any function, if summation is there, this is nothing but min term. 0 comma 2 comma 5 comma 7 comma 8 comma 10 comma 12, something is given like this. If someone is asking you to find what is the max term for this, this very simple. So what are the things which is left over here, that are comes under the max term. So before that, you want to find what is the maximum combination. Here they are using 4 bits. Okay, because the maximum value is 12 in your min term. So 4 bits means 0 to 15. So the left portion, so 0 is there, so 1 is not there, so which comes in your max term. 2 is there, 3 is not there, 4 is not there, 5 is there, 6 is not there, 7 is there, 8 is there, 9 is not there, 10 is there, 11 is not there, so 11, 12 is there, 13, 14 and 15 is not there. So which these things comes in under your max term. So like this you can represent. So only one thing you want to remember, SOP or POS. Okay, min term or max term. This is nothing but standard form. So this is a standard form to represent any digital output equation. So to just tell represent the output equation, we will use the this way of, okay, this is in standard form. Again there is one more thing called canonical form. So canonical form is little bit different actually, where you won't have any so that is not a simplified form. Again I will tell you, this standard form is also not in simplified form. Again you want to take k-map, you want to achieve k-map kind of things to get your simplified equation. Okay, but canonical form, it won't be in simplified manner. I will tell what is canonical form quickly. So canonical form is nothing but all literals must be there. All literals. Example, let I consider a function which contain the variables ABC, and I have an equation called a bar b. This is one function. Here if you see, there is one literal is missing, which is nothing but C is missing, and here A is missing. But my equation must contain all literals. If it contain all literals, then it contain that is called as canonical representation, canonical form of representation in a equation. But this is again doesn't make you any sense, because the missing C and A, if you add, your equation will get complex. But ultimately in our digital electronics, the concept is we want to reduce our complexity of equation. Again, for reducing the complexity, we are using Boolean algebra concept. In Boolean algebra concept, again, the user may find some issue like complexity. Like someone will apply Boolean algebra like concept, and he will keep on reducing the equation, and he may think this is the reduced form of equation, and he may stop there itself. But actually it may go three more steps, and we can reduce furthermore also. But ultimately he may think this is the reduced form, and he can stop there itself. This is one drawback of Boolean algebra. So again, for the overcome this, we are using k-map, where in k-map you'll get reduced form of equation, right? Okay, so we are achieving the reduced equation form, but ultimately adding one more literal to your equation is a stupid thing. But I will again tell you like what is this. So here, if I write this equation, a bar dot b dot 1 plus 1 dot b bar dot c, my equation is not going to change. This dot 1 multiplication with 1 will never affect my equation, right? It will remain as it is. So in place of 1, I want to substitute my missing literal, which is nothing but c. How I can substitute? So a bar dot b. So here in 1 I will substitute c plus c bar. So this is OR law, means generally in OR gate, if you do 1 plus 0, your output will be 1, which is nothing but c plus c complement. C complement, you will get output this one. This is the OR law actually. So here you can substitute, this is nothing but C only, right? So I can write a bar dot b dot c. Okay, same here also. What I can do, instead of 1, the a literal is missing, so a plus a bar I can write dot b bar dot c. Anyway, finally you will get a dot b bar dot c. So this is how they will represent, and this is not your reduced form. This is in simplified form. This is not a simplified form. If you look, the input expression is a simplified form, and after converting into canonical, this is not a simplified form. So only these things you want to remember. Even and different using if you are aware of Boolean algebra, like different place to add the literals. We will use different laws to add that literals. That's it. Got it? Huh? Any doubt is there? Abhishek, Bogala, you can give some thumbs up if you got. Okay, fine. Fine. So tomorrow I will target quickly about K map and gates and universal gates and all about direct circuits, combinational circuits. That's it. Like off adder, full adder, full subtractor, off subtractor, mux, demux, encoder, decoder, priority encoder, and we have comparators. So we'll complete this actually, and we'll target this for our tomorrow class. And as the part of tomorrow class, we will try to complete the combinational circuit. Like we are go through every combinational circuit. So I'm just putting like a revision all our digital parts. That's it. Its ultimate aim is not to give a detailed explanation. That's the reason I am going with some speed, right? Like this won't be there in Verilog. Like in Verilog, I will tell each and everything in slow manner. So only for digital electronics, I am covering this much speed actually. Okay. If you have any doubts or any anything, any suggestion or any drawbacks for from my side, you can ping me now, or else we will end today's session. So Abhishek, may I know, like you already have some knowledge in Verilog, right? Like even vocal. Okay, fine. So we'll continue tomorrow. If there is no doubt, we can end today's session. Thank you. Thank you.